Welcome to Microlecture 50, continuing on with our alkene addition reactions. This one is catalytic hydrogenation. Okay, so we're going to talk about the addition of H2, hydrogen, with palladium over carbon, which is a hydrogenation process. And if you've heard of hydrogenation of oils, for example, hydrogenated fats, that would be this process. It doesn't have to be palladium, by the way. It could be platinum, it could be rhodium. Okay, so there's other transition metals that can be used instead of palladium, and the chemistry works exactly the same way. So we want to be able to draw out, again, a transition state structure, and that's going to help us understand whether the addition of the hydrogens across the double bond are occurring syn or anti. And then, as usual, we'll want to be able to predict the product as being chiral or achiral. So first, let's just predict the product here, and kind of, I'll share the regio and stereochemistry details with you. So the way this is going to work is that hydrogen is going to add syn across the double bond, one hydrogen to one carbon, the other hydrogen to the other carbon. In this case, that will force this methyl onto this side. And then on the other carbon, you've just got hydrogen atoms, right? So these hydrogens must add syn to each other, and with equal likelihood, we could have had those hydrogen atoms add both of them on the wedge. Okay, so we do have a stereocenter right there, but we form a 50-50 mix of enantiomers, so a racemate, and so it's achiral. All right, let's practice this Syn addition with a couple of more, and then I will share sort of the transition state structure and explain why it's Syn addition. So with the next one, we've got a 5-membered ring, and we know that the hydrogen atoms are going to add across on the same face, Syn addition. So in this case, that's going to dictate that the methyl and the ethyl are on dash, but with equal likelihood, because this structure is flat, it could approach the palladium over carbon from the opposite face, right? So, and I'll explain that more in the mechanistic details. So the opposite side is also possible, and so hydrogens could have both added on dash, forcing the ethyl and the methyl forward, like so. That's a 50-50 mix of enantiomers, so it's a racemate, so it's achiral. Let's see how it plays out here, where we've got a group, a nearby group, on one face. It's on the back face of the double bond, the dash side, not the wedge side. It's going to prohibit the molecule from approaching our reagent on that back face, okay? So when I draw my product now, I'm going to be careful to show this tert-butyl group exactly where it is, and show that the hydrogens that add must add on the opposite face of that very large group. That's going to force these methyls to be on the same side as the tert-butyl. Okay, so H's add on opposite face of nearby R groups. The result is that you have a chiral product. We get this, not the H's adding to the dash side. Okay, so the other stereoisomer does not form. Chiral product, chiral starting material led to the chiral product. All right, so let's think about the mechanistic details in both cases here to try to reason why we would have an achiral product in one case, but a chiral product in the other case. So remember that these alkenes are flat, all right? And this reagent that we're using it's a heterogeneous catalysis. It's heterogeneous means that this guy is on solid support, and the sample above it is in liquid. So heterogeneous means we've got both liquid and solid materials reacting with one another in different phases. All right. So our solid support can be drawn like this. Okay, that is charcoal, essentially, carbon, coated with palladium or platinum or another transition metal. And along the surface of this solid support, we have hydrogens being provided. Okay, and so this molecule is going to approach. It's flat, okay, and it's going to approach. So it could approach from this face and pick up a couple of hydrogen atoms. So there and there. Meanwhile, the double bond is half broken. So the double bond is half broken. And the bonds to the hydrogen atoms that we're picking up from the surface are half formed. Okay, so there's this sort of transition state structure there. But with equal likelihood, we could approach from the opposite face. Okay, in the next example, we've got the same sort of thing. Okay, but when the double bond approaches, this time it's got on the back side of it, so up here, it's got a tert-butyl. All right, and so only the bottom face can react in this case, or only one face can react. And so we get a transition state that looks like this, but we don't get the other event happening. So the tert-butyl group is going to block the top face of the molecule, and so this molecule can't interact with the surface from that direction. Okay, whereas in the other case, both top and bottom face can approach. So that's what I mean by transition state structure, the half-formed bonds to hydrogen and half-broken carbon-carbon double bond, to show the Syn addition and to show that nearby R groups are going to dictate the stereo